Good afternoon, all. Welcome to the Samvad talk on energy costs and indoor comfort management in semi public buildings by Pradnya Gaunkar. I'm Shivangi Garg with the Branding Committee, and I'll be introducing the speaker for the day. Pradnya Gaunkar is a full time research scholar in the Networking and Communication Research Lab of IIIT Bangalore. She received her MTech in Networking and Communication from IIIT Bangalore in 2012. She worked as a scientist in the Industrial Communication Research Group of ABB Bangalore from 2012 to 2015. She was an intern with the Speech Processing Group in Siemens R&D Bangalore. She has also worked with Engineering College, Goa, as a lecturer from 2008 to 2010. Her research interests include Internet of Things, wireless communication, sensor fusion, optimization, energy efficiency in smart buildings. In today's talk, we will talk about semi public buildings, which are privately owned large commercial buildings meant for public use, such as gyms, shopping malls, movie halls, etc., which thrive on footfall. The equipment in such buildings, like the conditioning units, dehumidifiers, air purifiers, lights, etc., must run continuously during operational hours to ensure customer satisfaction. However, this heavily contributes to the energy bills in buildings, making them one of the highest consumers of energy in the world today. These buildings, being non residential in nature, the occupants are far less concerned about the energy consumption. It is thus the responsibility of building owners to manage energy costs and comfort. In this talk, we will explore various aspects of simultaneously optimizing both energy cost and occupant comfort in buildings. With several challenges at hand, the research goals include understanding energy cost and indoor comfort, investing the impact of ambient parameters, occupant behavior, geographical location, energy budget setting, and occupancy levels on the same. The envisioned impact of this work includes enabling operators for efficient building management while providing desirable comfort to occupants customized as per their behavior and requirements. The faculty in charge of NCRL is Professor Jyotsna Bapat, who currently serves as the Dean Faculty at IIIT Bangalore. She's been a faculty member at IIIT since 2006. She has received her PhD from Penn State University. After graduation, she worked at Bell Labs, NJ, and Fairleigh Dickinson University, NJ. Her areas of interest include wireless communication, massive MIMO, privacy and security for IoT, energy savings. She was PI of sponsored projects from NXP, Honeywell, and Co. She recently completed a joint project with University of Twente, Netherlands on privacy-aware smart buildings using IoT. We warm-heartedly welcome faculty in charge of NCRL and Pragna Gaunkar to deliver a talk on energy cost and indoor comfort management in semi-public buildings. Before we get started with the talk, I would like to thank the audience on both the Zoom meeting and YouTube live stream for attending the talk. On behalf of the Samvad team, please feel free to ask your questions in the chat boxes. We will take the questions at the end of the talk. Now, I would like to request Pradyan Gaunkar to begin her talk. Thank you.
Thank you so much, Shivangi, and welcome everybody to the talk today. I'm Pradnya Gaukar, and today I would be talking about our work on energy cost and indoor comfort management in semi public buildings. So, let's get started. This is the brief overview of the talk today. We would be looking into the details of Project COPAS, just an overview, sorry. Then we would be looking into the concepts of smart and green buildings. We will be also looking at the two main objectives of energy cost and indoor comfort, which on which the optimization models in smart buildings are developed. We will be looking into the proposed approaches as far as this work area is concerned, and then we would be looking into the conclusions and future work. This work is being supported by Ministry of Electronics and IT, Government of India, and is in collaboration with University of Twente, the Netherlands, and Cognizant Inc. India. Okay, so let's get started. Let's have a overview of Project COPAS first. So Project COPAS is Cooperating Objects for Privacy-Aware Smart Buildings. The objectives of the project include design of privacy-aware smart buildings with focus on energy efficiency and user comfort. These two objectives are the ones which are very important today as far as the smart buildings and smart connected community paradigms are concerned. The objective two of the project was to propose an overall approach for smart energy management in semi-public spaces. Now, semi-public spaces include buildings such as hotels, hospitals, educational institutions, malls, shopping malls, etc. Based on and This approach is to be proposed based on users' presence, the expected behavior, mobility, and usage patterns. Right. So these are the things which are very much variable in any smart building environment. Other cross-cutting concerns include privacy, reliability, and safety. Now let's look into the expected impact and the focus of our work. The expected impact include the improved quality of experience for users and comfortable environment based on the situation. So as far as these buildings are concerned, we can see that they majorly thrive on footfall, right? The number of people who turn up into the buildings, and this is directly connected to the profits that are made by the buildings for the operators, correct? So they might be government owned or they might be public owned, but they are majorly profit oriented. So providing quality of experience for the users is very important, right? So based on the situation, we need to make sure that they get the desirable quality of experience, but this is with least intrusive automation, right? So making sure that the automation is least intrusive and also they are provided with the privacy that is required. The other expected impact is to provide optimal usage of resources, including data, energy, and personnel. So, the other concerns are regarding the occupancy management, safety, and evacuation. So, all these things are covered into the impact sphere. Now, as far as our work is concerned, we majorly focus on the development of mathematical models for optimization of energy cost and indoor comfort. Now, indoor comfort majorly consists of these three dimensions: thermal, air quality comfort, and network related comfort. By network, I mean the internet connectivity in the buildings. We also have looked into the impact of geographical location based parameters on the two important objectives of energy cost and indoor comfort. Further, this work also investigated the impact of energy target budget setting on energy cost and indoor comfort. We will shortly look into what energy target budget setting means, and we'll get into the details of it. So, with this in mind, let's start with the actuals of the talk. So, first, let's look into the concept of smart and green buildings. We have been hearing these terms quite often today, right? So, but then smart and green buildings are a bit different from each other. Like, we'll see how. Smart buildings are enabled with the integrated technology. This is something which we all know. It also takes into consideration the aspects of occupancy management, that is majorly concerning with the people in the buildings, the number of people majorly, and their activity, and they strive for operational efficiency, right? But green buildings are the ones which are considered successful at implementing resource efficiency and have shown improved performance. There is a body which looks into the certification, verification, and certification of buildings from basically, they are termed green only when a body called LEED, Leadership in Energy and Environmental Design, provides them with a certification. Correct? So this is a small diagram which shows you what are the different aspects of green buildings and smart buildings and what things they have in common, correct? So as you see on the extreme left, indoor environment and comfort, energy, water, materials and resources, design and innovation, along with uh, optimization methods, monitoring systems, measurement, commissioning, and control systems are the aspects of green buildings. And when the building has all these things in place, is when they kind of are given the certification by LEED. The other aspects that make the building smart are basically related to the automation and technology that is there in the buildings, which majorly consists of the HVAC or the AC units, lighting, power, etc. So, this is what smart and green buildings are in a gist. So, moving on to the other important aspects of smart buildings today, which is Internet of Things, correct? Now, IoT or Internet of Things is majorly in place today to enable buildings with technology and integration, right? It includes the data network, the voice and video systems, the communication backbone, the things which are majorly concerned when we want to kind of have connected type of a community today, which means one building has connectivity within its internal spaces, and it is also capable of communicating with the other buildings in the vicinity if required, right? Not only this, but it is enabled with data collection from other group of buildings in order to make sure that optimization strategies are in place, leading to a sustainable community. Other terms that you might have heard regarding usage of Internet of Things in buildings are data analysis, software and cloud computing for policy making, security and privacy, of course, energy saving, and integration with the power grid, right? So all these aspects are covered under the umbrella of Internet of Things. Moving on, now when we say we are talking about smart buildings, the other thing that comes into picture is something called as the building envelope, right? And its thermal performance. Building envelope basically means the outermost structure of the building, which includes the roofs, the walls, the windows, doors, etc. Why this leads to the idea of thermal performance of the building is because a building is largely affected by its environment. It's not a standalone system, it is continuously interacting with the indoor and the outdoor conditions to which it is subjected, right? The envelope is responsible for maintaining the thermal balance within the buildings, and this is called the thermal load. You might have heard of terms like convection, conduction, radiation, evaporation, etc. As far as the various processes in the space are concerned, all these are applicable to how the building interacts with its environment, and they directly determine the performance and the efficiency of the building. So, the other immediate effect of this is that it influences the choice of heating, ventilation, and air conditioning units in the building, right? So, depending on how big is the building, what are the types of materials used in the building, what are the number of doors and windows, whether they are glazed, unglazed, etc. All this helps to figure out the capacity and the performance of the HVAC unit that needs to be installed in the building. So it directly implies that careful design and construction of the envelope can ensure efficiency and user comfort both. As I said, the factors that affect thermal load include externally the roof, walls, windows, doors, floor, etc. And the internal factors include lamps, the equipment which is running in the building, occupants, and their activities, because all this basically goes through the different processes, physical processes in the building, which are responsible for generating heat in the building, right? Which contributes to the thermal load. Okay, so yeah, so this picture explains the um, concept that we just introduced about thermal performance better. Um, Figure 2A talks about the building and the external environment. Like you see, the roof is exposed to radiation, the walls are exposed to solar radiation. There is conduction that is happening between the surfaces of the external air and the roof, the walls. There is also convection that is happening through the walls, and there is this AC unit which is running continuously in order to provide comfortable environment to the users inside the building. So there is a lot of mechanical work that the AC is doing, right? All these things contribute to the thermal load. Now, when it comes to the internal factors, the human beings who are present inside the building, the lamps, etc., they are also kind of continuously operating and affecting the indoor environment. So that you can see in figure 2b. All these processes are kind of affecting how the thermal load of the building is being calculated continuously, right? Now we get into the two objectives, important objectives of optimization in buildings, which are energy cost and indoor comfort, right? Let's first look into the parameters that affect energy cost in buildings, right? So as I said, HVAC units are the ones which majorly contribute to the energy bills today in the buildings. The other uh, uh, equipment or group of equipment which is actually affecting the energy cost is the lighting equipment, but it's not as much as the HVAC system. So majorly works focus on calculating the energy cost of the HVAC systems today. So it requires us to describe relationships between the demand and supply of energy from various sources that comes to the building, right? So it might be the power grid, the solar energy, you have the backup batteries, etc. Other factors that are included are how the energy is being built in the given geographical region, right? So, what is the cost per kilowatt hour unit of the energy? So, like we have the slab wise billing that happens in India, there are also other types of strategies which are adopted in other locations, which include real time rates, the peak time rates, etc. And these keep changing based on the seasons or even maybe the time of day. So all these parameters are important when it comes to the calculation of energy cost in a building. Further, looking into the indoor comfort and parameters. So, generally, indoor comfort includes all those factors which make a person feel comfortable in a building. So, the first thing that comes to our mind is the temperature and the relative humidity, right? And yes, these aspects are directly contributing to the thermal uh, comfort dimension of the building. The other factors that affect comfort are light intensity, the smells or the odor in the rooms, the CO2 or the carbon dioxide levels, etc., which respectively form the parameters which affect the visual and the olfactory comfort of users in the building, right? So it generally means that all these parameters, ambient parameters, have to be maintained at a desired level so as to have a comfortable environment for the user. The other thing that affects indoor comfort is the people and their activities, because this will directly contribute to how the person is feeling at any given point in time, and it might differ from one person to another. So it's quite subjective in nature, right? Also, the type of clothing that a person is wearing in a given building for the kind of a purpose that the person has been to that building, right? So, if a person is visiting the shopping mall, the person might be wearing very casual clothes, whereas if he or she is in a gym, the kind of activity that the person is doing is very different, right? So, all these factors come into picture. The other aspect that affects indoor comfort are the type of models that people have proposed today in literature, right? So, one of the existing models is the Fanger's predictive mean vote model, which is called the PMV model for short, and its variants, right? So, this is one of the oldest model that is there in place today, and a lot of variations have been made to these. There is also an air quality model that is proposed by Fanger and which is widely used today. So we will look into both these things in some time. The standards that take care of indoor comfort in buildings include the American standard called ASHRAE, the international standard ISO, and the European standard of SIN. One more important thing that I would like to mention here is Of late, we have seen the dependency of occupants on internet connectivity, right? While in any kind of a building. So, in our work, we have also tried to include the quality of experience of internet connectivity as part of indoor comfort for the users, right? So, we have introduced another dimension to comfort, which is called the Wi Fi comfort. We will also look into this work shortly. Now, with the idea of indoor comfort and energy cost in mind, let's look into the details of optimization models, right, that are in place in buildings today. So, as you can see, we are dealing here with conflicting objectives, right? So, as far as the operator of the buildings is concerned, they would like to minimize the energy cost that is incurred onto the building at any given time. Whereas, as far as the users are concerned or the occupants are concerned, they would want to have maximum comfort. So, uh, definitely, there is a need to optimize between these two things. Um, so when we are considering so many parameters and objectives, obviously this model is a multivariable, multi-objective type of a model. And based on the complexity of the model, we choose the solution strategies to deal with the model, right? So the other important aspect that comes into play here is the Pareto optimal solution. So obviously, when you see the conflict in between these two objectives, we know that there is no single solution that can help us to, solve this model, right, or the problem. So in one of our works, which is a survey on the different types of optimization models in place today for buildings, we have tried to categorize the different types of strategies used for finding solutions to such problems, right? So you see that there's a huge bag of optimization strategies here, which goes from direct search to integer programming to the meta heuristic type of algorithms that we have today, right? And the stochastic population based ones, which are very popular, including the evolutionary type or the majorly the GA and PSO type of algorithms, right? So this is just kind of one figure in which we can include the variety of solution strategies adopted today for the optimization models in buildings. Yeah. So, what is the exact problem that we're dealing with as far as our work on this, optimization strategies for buildings is concerned? So, we have looked into the system modeling and optimization of energy efficiency and indoor comfort for both public as well as semi-public buildings. We have majorly looked into aspects of you know extending the traditional optimization models for energy and indoor comfort to include, first of all, the location related factors such as the energy price and the building strategy, the outdoor temperature, and the clothing. So as you see, these three factors directly are the result of the geographical location of the building, right? Secondly, the occupant's behavior and occupancy patterns, which are very much variable in nature, right? So, um, what are the challenges which we have kind of tried to address in this work? So, basically, as I said, the dynamic nature of indoor environments, which arises from the occupancy, heat load, and occupants' behavior, the non-linear energy costs because of the location and the government regulations, equipment usage, etc. And of course, because of the subjectivity involved in user comfort, the complexity in just expression of user comfort on its own, because of the factors we just saw earlier. Okay, so let's look into the proposed approaches as far as the project and this work is concerned. So I have kind of created three subtopics here so that we can look into the contributions of the work individually. So first we will look into the location awareness and multidimensional comfort. Then we will talk about the energy budget concept and the optimization model that we have proposed, taking into consideration this concept. And as I said earlier in this talk, we have also introduced another additional dimension to the comfort part of it, which is called the Wi-Fi comfort. We will also look into that work, right? So, yeah, let's first look into location awareness and multidimensional comfort. So, this is an overview of what we are going to, discuss further in the slides. So, you see this small dotted orange line, which basically says that, there are two sub models of optimization that we are going to speak about. The first one, that is the optimization model on the top here, which takes into consideration the two objectives, the energy cost and the thermal discomfort. They depend upon these factors that are listed here, right? So the energy price and the targets, the building structure related parameters, which we have already discussed, the equipment, etc. The other type of the category of input is basically everything that is affected by the location, that is the temperature, the occupancy, clothing, and activity, right? These form the energy cost and the thermal comfort objectives, which are optimized, and the output of this model include the desired comfort, the target energy cost, building management guidelines in general, right? The other optimization model that we are working on is basically, it's an extension of the previous optimization model here to include the additional dimension of air quality comfort, as you see here, right? So um, we see that air quality is majorly affected by two factors in a building, right? So the first factor is the carbon dioxide emission, and the second factor is the indoor furnishings, which are subjected to a certain temperature and relative humidity, which, when subjected to relative humidity and certain temperature, give rise to some sort of pollutants which are toxic in nature, and hence they affect the indoor air quality, right? So these form the three conflicting objectives for the optimization model, and the outputs basically are the same like in the first part, but with an additional dimension of air quality added to the results. Okay, so with this in mind, let's see what location awareness and multidimensional comfort for the first model include. So, as I said, occupants' preferences of clothing and activity depend on the local weather and the type of the building, right? So, this is a glimpse of how our energy cost function might look like. This is a curve fit model that we have proposed here. You see that the slab wise energy tariff, which is existent in India today, is taken into consideration, right? So, it's a polynomial fit that basically depends upon uh, the energy tariff in the region. So, this is the energy cost function part of it. As I said in the earlier slides, predictive mean vote model by Fanger is considered as one of the standard models for indoor comfort or thermal comfort today. It includes all these factors, right? There's a big list of factors. It includes the air temperature, the mean radiant temperature, air velocity, partial pressure, the metabolic rate or the activity of the person, the clothing insulation factor, etc. Right. So with all this, we can get a clear indication of what might be the estimate uh, of indoor thermal comfort that we are looking at any given time for a particular group of people. Right. So uh, we have used this particular measure or index of PMV in order to define the thermal discomfort this way, right? So we have described discomfort D as PMV square, right? And the comfort model for it has been proposed based on the control variable, which is T set. T set is the temperature setting or the AC setting in the room or the building. So we have used the weighted aggregation method in order to solve this, which includes, providing each of the two normalized values of the objectives EC and D weighted in a particular way. That is, W1 and W2 is equal to 1, right? So they are provided with weights such that they both equate to 1. So according to the preference, whether you want to kind of make sure that your solution is energy cost centric or the occupant centric, you can accordingly vary these weights so as to have a customized kind of a solution, right? So some results that I would like to share over here include, first of all, the subplot on top here, top left, shows you the inherent conflict between the two objectives, that is the energy cost and the discomfort, right? And that is with respect to the HVAC temperature setting in the building. Secondly, as I said in the previous slide, depending on the weights, that is W1 and W2, you can have different types of solutions, whether they are energy centric or discomfort or comfort centric, depends on whether the occupants are looking it, whether it's from the occupant's point of view or whether it's from the operator point of view. Also, the Pareto front for the Pareto optimal solution based on the control variable T set is also shown in the subplot here. The extension of this work to include the effects of you know uh, temperature and relative humidity on indoor furnishings such as carpets and paints has also been looked into. So this basically, the emissions from carpets, paints, sealants, PVC, etc., which are used as furnishings in the buildings, directly contribute to the indoor air quality. So, as per Fanger's model of indoor air quality, there is an index which he puts forth, which is called as the acceptability of air. So, based on the acceptability of air, majorly you can describe the discomfort due to indoor air quality in a building. So, the objectives that we are majorly looking into are these three, right? So, this is work in progress. So, yeah, so basically we follow the same sort of process in order to arrive at the Pareto optimal solutions. Yeah, now let's look into the second sub area, which is the energy budget constraint comfort optimization model, right, for energy efficient buildings. So, as I said, there's a concept called as target budget setting for smart buildings, right? So, if the operator wants to set a particular energy budget for the building, he or she can do so based on, whether it is for a few months or for the whole year or for a few weeks, etc. So, this can be done based on the volume of the building, right? So, basically, you need to know how the energy prices in the region are, and you need to kind of do a small survey in order to see how you can set a particular energy budget which you don't kind of cross at the set time in that particular region. Obviously, the ambient parameter that we have considered over here, the dominant parameter, is temperature. The optimization model again is based on two conflicting objectives of energy cost and thermal discomfort, right? So, yeah, the optimization model looks something like this, right? So, we have developed it based on the difference in the temperature Ts and Tc. Ts is the set temperature of the HVAC, and Tc is the temperature which we call the temperature, which is desirable by the user. So, more the difference between these two temperatures, basically, it directly affects how the person is feeling in the room, correct? Now, C is the comfort. We have kind of, used only one parameter, as I said, as a control variable, which is TS, or the setting of the HVAC unit in the building. So as you see here, it's a constraint model, and EC, or the energy cost, is always required to be less than or equal to a value M, which is the maximum energy budget, which is set for the volume of the building, which is in INR per meter cube. Okay, so this depends on the size of the building. So as you see, as a constraint model, we have used the Lagrange method to find the solution to it, and you see that it is dependent on the value of M, which is the energy budget set for the building. It is evaluated for two scenarios. First of all, the cooling scenario, and then the heating scenario, depending on the weather, right? So majorly, it requires you to figure out what is the TS, or the best setting of your AC that is required in the given season. Okay, so this result kind of shows us what we are looking into as far as the optimization model is concerned, right? So the contour plot is basically for the user comfort, right? So considering that an outdoor temperature, the outdoor temperature varies from 0 to say 40, and we have set some reference temperature as the comfort temperature of the user, which is Tc equal to 20. As you increase the energy budget M, the comfort, or the user comfort, is seen to kind of get better, right? The scale is from 0.1 to 1. So at about 600, the value is actually seen to be the best, which is equal to 1, right? So yeah, so we also have kind of tested this using a small test bed in the lab. So this is the uh, you know um, testbed that we have developed, which includes the different sensors for temperature and relative humidity sensing. And it also has other sensors which can be used for air quality monitoring, etc. And this is quite extendable, so we can include more sensors on it. Okay. Now moving on to the third sub area, which is the prediction of network or Wi-Fi comfort, right? So we might have heard of terms like quality of experience of Wi-Fi when it comes to describing the connection in any building, right? But including it as part of indoor environment quality in buildings is something that was not looked into, and we have tried to include it as one of the dimension of comfort. So, yeah, this is the overview. So, we have looked into aspects of the building which are quite variable as far as the Wi-Fi discomfort or the comfort is concerned. So, what are the things that affect uh, this dimension of comfort? First of all, the occupancy, right? So, whether the person is sitting in a place and accessing the Wi-Fi, or whether the person is mobile. Secondly, what is the kind of location? Does the person experience too many drops of connectivity, or it's seamless? The Wi-Fi RSSI, right, the receive strength indicator, or the power of the Wi-Fi that a user receives at any point in time, and of course the time for which the Wi-Fi is in use, or the user is using it for specific type of a service or application, right? So we have kind of used the classification model to kind of describe comfort and find out the quality of experience of comfort in a building. So the general outputs again include the desired comfort, target management cost, and building management guidelines. Okay, so as I said, um, indoor comfort is significantly influenced by the quality of Wi-Fi today. Wi-Fi signal strength, Wi-Fi access permissions, steady state occupancy, and applications used by a person anytime in a building directly affect the Wi-Fi comfort. We have presented a case study with three applications in place. Like, we have tried to work with a use case which is mostly for an office type of an environment, wherein the occupants might be expected to, work with email, voice, or video, right? The classification methodology that we have used over here is the support vector machines method. And we have used the comfort levels to be just binary to start off with, because this was like the feasibility study and understanding the whole concept part of it. But this obviously can be extended to include more classes of comfort at any given point in time for the different categories of applications. Now, the choice of SVM was kind of because it works well with binary classification problems on both low and high dimensional data sets, right? Also, it handles the linearity and non-linearity of sets well, obviously with a proper choice of parameters, and yeah, of course, with balanced number of classification labels. So we have tried, working with three data sets, which are basically Wi-Fi fingerprinting data sets, which were available from UCI, IEEE data port, and also we have collected data from our own institute for this purpose. The fine tuning of the hyperparameters of the SVM model was done based on the grid search algorithm, right? So C, gamma, as the hyperparameters, they were decided only after fine tuning using the grid search algorithm. So this is just a glimpse with, a glimpse of the um, results that we obtained of this from the study. Um, the first one that you see over here in figure 10A is the receiver operating characteristics. It's a plot of the true positive rate and the false positive rate that we obtained for with the data set. This is with the UCI data set, because we found that data set to be the most balanced data set amongst the three. As you see, the area under the curve when it comes to the blue line here, which is SVM with grid search, is much better, that is 0.99. Whereas with untuned parameters of SVM, we see that the area under the curve is quite poor as compared to the blue one. The other way of expressing the quality of experience, or QoE, was to show the system performance with respect to the number of APs, or the access points in the room or the building, right? So We have done this for two applications or services. First of all, email, and second one is the video stream, right? So obviously, it goes along with our intuition, where we see that as you increase the number of APs in the room, the quality of experience that is seen by the users increases. So yeah, so this brings us to the conclusions and future work. As far as the conclusions are concerned, we have explored scenarios in public buildings and evaluated them to propose energy efficient optimization models for user comfort. Impact of factors such as location, energy budget setting, and Wi Fi connectivity has been investigated. And possible extensions of the work include, you know, proposing additional dimensions to comfort with focus on light intensity and audio levels, inclusion of energy consumption of humidifiers, which become an important aspect of HVAC today. Like it comes integrated with the HVAC. So looking into the cost model for that also becomes an important aspect. And integration of smart building models with smart grids, right? So this is another important area where people are moving today. So yeah, this also could be a possible extension of the work. And more deployments and tests in real use case scenarios in buildings to get a practical feel of the work is also something that can be looked into. So these are some of the references, and that brings us to the end of the talk. Thank you. And if there are any questions, I'll be happy to take them now.
Thank you, Pratnya. It's a
Thank
wonderful talk. There's a question by Prasanna.
you.
Do you do optimal power flow with nonlinear constraints?
Optimal power flow with non-linear constraints is something that we have looked into as far as the work in literature is concerned, but as far as our work is concerned, we have not taken that into consideration yet. But yeah, that is also an important aspect. Yes.
Okay. So, Pragna, you had mentioned that you had taken a lot of experimental results from our campus and other places for your work.
Yes, ma'am.
So, how do you conduct these experiments?
Yeah, so, ma'am, there are like three categories of experiments that we basically did. One was for the occupancy detection and management, right? So that was one part. Second one was for the thermal comfort, and the third one was for the Wi-Fi comfort.
Right.
So all this basically required us to build our own, test beds for
Okay.
the required purposes. So we basically had to go through the whole process of choosing the sensors and the controllers, which included Raspberry Pi, etc., and
Okay.
testing it out in first of all the lab environment to just see whether they are working or not on the given platform, whether they're collecting data the way we want it from a particular zone, etc. And
Yeah.
then slowly kind of scaling it up so that one particular floor of the building was taken into consideration, then we scaled it up to two floors, etc. So yeah, so we actually went from the process of developing our own test bed to doing the data collection and the analysis.
Right.
So yeah, basically we wanted to have as much of data as possible, not only
Oh,
the ones that are available online, but also something that's quite unique to the institute as well.
right. Right. So, in terms of collection of data, so how many days did you collect, and does that variable matter, or
Yeah.
across hours of the day and all of that?
Yes. So, see, it depends on what you're collecting the data for. So, say, for example, it was regarding the occupancy management application of the work. Then,
Mm.
yes, we did keep the, devices
Time of
on,
the day.
yeah, throughout
Okay.
the day to see the pattern of
Okay.
occupancy.
Okay.
But generally, that might not happen in a use case scenario for a actual semi-public building, like say for example a shopping mall, which it might have its set operational hours like 9 to 9 or something like that. So it
Right.
depends what application you're looking into. So
Okay.
yeah, we did do this over like a few weeks also for certain applications like the thermal comfort management part of it. We did run the test for more than I think 2 weeks to 3 weeks.
Okay. 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 So if you have so for 2 weeks, uh, what was the size of the data that you would have gathered? How do you manage large scale data?
So
Because
we had the ELK, that is the Elasticsearch Logstash available with us. So we used to store
okay,
data there.
okay,
Also, some of the data was processed online and some of it was stored in the repositories. So actually, I think our idea was to collect at least a minimum of 2 GB of data, so as to have an idea of the different times of the day, to cover
oh,
the different times of the day.
okay.
Yeah.
Uh, Professor Dinesh has asked how are privacy concerns addressed here, and Prasanna has asked about scalability of your experiments, I suppose.
Yeah. So I'll
Just one this one.
yeah.
What are privacy concerns here and how they are addressed?
Yes, sir. So one of the aspects that we are looking into as far as privacy is concerned is, like, say for example, we want to determine the occupancy in a building with respect to, the thermal comfort management in a building. We would want to make sure that we are making use of sensors which are privacy aware. Like, if you're making use of sensors such as cameras or video, etc., it basically is considered to be intrusive today as far as humans in the building are concerned. So we have tried to use sensors which are low cost and privacy aware, such as the PIR sensors and the door sensors, etc., with minimal intrusion of privacy. So that is one of the ways in which we are addressing concerns with privacy. There is also, the larger idea of, privacy of data, etc., which my colleagues are looking into as far as this work is concerned. And, it's a part of Project Copas, but yeah, so my colleagues are also kind of, looking into it. Yeah, so that's about privacy part of it. Scalability of the experiments, yes. So our models are quite generic, which can be, in my opinion, can be scaled up to a building environment under consideration. So if we want to kind of test it out for a larger building, we can do it by just taking into consideration the various factors of size and the structure in itself of the building. So if that was what was expected as far as scalability is concerned, then that's what comes to my mind as of now.
Okay, just a related one.
Yes, sir.
See, in the scalability I'm talking.
Yeah.
Uh, Intrinsically, isn't this problem not scalable? What I mean in terms of this thing. For example, if you are looking at a smart building requirements in, say, in Netherlands
Yeah.
versus a smart building requirements, say, in Chennai. Okay,
Mhm.
the one is the weather conditions themselves are so different.
Right.
Probably the various priorities you may have to put, uh, they all differ even from definitely from location to location. I mean, in terms of, like, is a desert type of thing, like Dubai or like that, or uh, like Bangalore and things like that. Uh, uh, so, like, for example, Terry constructs the buildings which are cool without using any AC,
Yeah. Right.
where they look at purely this thing, the local type of conditions, and the material that is used.
Yes.
So in that sense, probably isn't it that each place, each size, each building have its own solutions rather than scalable? But I mean, I may be wrong.
No, I think yes. I mean, that is actually what we are also kind of saying. So the geographical location as a whole has a impact on how you develop this model. So as you rightly said, the location directly affects the parameters that you just said. So yeah, it does mean that it on its own it is scalable to kind of include all these parameters. Yes.
If I
See,
may, this is Professor Bapat, if I may join. But the
yeah,
Pradnya model essentially will take into account the local conditions as well as the local requirements. As Mr. Dinesh
Yeah,
has said,
yes.
requirements in Chennai will be vastly different from requirements in Netherlands, and that's what is taken care of.
Yeah, yeah.
And Prasanna, for the, I'm guessing you're talking about the power flow, optimal power flow. Our this thing in Pradnya's work, she has strictly looked at the power requirements and the power charges that are present in individual countries and how they increase depending upon the kind of consumption that is present. Thank you. I think Pradnya, you have one more question.
Yeah,
Okay,
Jayati
yeah.
has raised a hand. Jayati, you
Yeah,
could ask.
sure. Thanks. Thanks, Pradnya. That was a very interesting talk. I had a couple of questions. So, first one was I was thinking, for example, in some situations, for example, when thermal parameter is being optimized, let's say the number of people coming and going out of the building keep changing. So, is it possible to for the model to come like continuously keep updating its learning and then updating its predictions and so on, where it continuously learns, or maybe it even matters in some other models as well, not just for the temperature.
Yes, I mean, yes. So that aspect of the models is kind of, included in the dynamic optimization type of models, right? So what I have used over here are still the steady state models, but in order to continuously understand the changes that are happening in the environment due to occupancy or even due to the change of weather conditions
Right.
locally, you need to take into consideration the dynamic nature of the models. Yeah, and yeah, that can be done.
Okay. Okay.
Yes.
Thanks. And yeah, one more question I had
Yeah.
was like, while optimizing, have you noticed like any parameters which are conflicting? Like if you try to optimize for one parameter, it starts affecting the another parameter and so on, where there is a conflict between parameters and so on.
Um, so you're talking about the control variables, or you're talking about the objectives on their own, right? So as far as the objectives of energy cost and indoor comfort are concerned, yes, there is an inherent conflict between the two. So
Okay.
yeah, that's the need for optimization, right there. So that is one thing. But as far as the parameters are concerned, if you're talking about the control variables, then we might not be directly able to justify the conflict between them. But yeah, in order to have the optimization strategy in place, definitely the single objectives that we are talking about, the cost and comfort, are conflicting in nature.
If there are no further questions, then we'd like to thank Pragnya for the wonderful talk. Big hand for you, Pragnya. Thank you
Thank
so
you,
much.
ma'am. Thank you, everyone.
And yeah, and thanks for having so many publications on this work as well. So yeah,
Thank you, ma'am.
congratulations.
Thanks.